Today we'll be discussing about single source shortest path algorithms. The shortest path algorithms work on weighted and directed graphs. As you might already be knowing, a weighted graph is a graph in which all the edges are assigned a real value called the weight. If you represent weight as a function, this is how you represent. Weight W is a function which maps every edge in the set of edges E to a real value in the set of real numbers R. Now let's consider the path P is equal to V0, V1, etc. up to Vk. The meaning of this representation is that P is a path from vertex V0 to Vk, and there is an edge from V0 to V1, there is another edge from V1 to V2, from V2 to V3, and so on up to Vk. In short, the intermediate vertices V1 to Vk minus 1 are written in the same order as they appear in the path from V0 to Vk. So if you want to find the weight of this path, all you have to do is find out the sum of the weights of all the edges included in this path, which can be formally represented like this. Here, W of Vi minus 1 Vi means the weight of the edge from vertex Vi minus 1 to vertex Vi. Now let's represent the shortest path from a vertex U to vertex V using delta of UV. Now there may be many paths from the vertex U to vertex V, and out of this, the path which has the minimum weight will be the shortest path from U to V. So this is formally represented as delta of UV is equal to minimum of W of P from U to V. Now if there is no path existing in the graph from U to V, then the shortest path from U to V is defined as infinity. Here we are discussing the single source shortest path problem, and this problem is to find the shortest path from a source vertex S to every other vertex in the graph. The common algorithms to solve this problem are the Bellman-Ford algorithm and the Dijkstra's algorithm. Out of this, we will be discussing the Dijkstra's algorithm. The Dijkstra's algorithm can be applied to directed and weighted graphs with non-negative edge weight. Initially, the distance from the source vertex is set to infinity for each of the vertices. The next step is to identify the vertices which are directly connected to the source vertex and then assign the corresponding edge weights to these vertices. Now identify the vertex which has the least value, and the value of this vertex is made permanent. Now recalculate the distance of each vertex from the source through the newly selected vertex. Update the values of the vertices only if the newly calculated value is less than the already calculated value. Now repeat the last two steps until all the vertices have permanent values. Let's discuss the algorithm with the help of an example. There are two methods in which you can represent the steps of the algorithm. The steps can be expressed as a graphical representation as shown on the left, or as a matrix representation as shown on the right. In this example, we take the vertex S as the source vertex. So we are supposed to find out the shortest distance from the vertex S to all the other vertices T, X, Y, and Z. In the graphical representation, the values written within the vertex indicate the distance from the source vertex. The distance from the source vertex to the source vertex itself is always 0, and hence the value 0 is assigned in the vertex S. For all the other vertices, we initialize the distance as infinity. The same information is represented in the matrix method as a row in the matrix. Next, we identify the vertices which have direct edges from the source. They are T and Y. Since the weight of edge ST is 10, the distance of T from S is updated as 10. Similarly, the value of Y is updated as 5. The updations in these values are shown as the next row in the matrix. Now identify the vertex which has the least distance from the source, which in this case is Y. So the distance of Y is made permanent. Now calculate the distance of all the other vertices from the source through the vertex y. So first let's consider the vertex T. The distance of vertex T from S through y can be calculated as the sum of the weights of the edges sy and yt, that is 5 plus 3, which is equal to 8. We can see that this value is better than the previously calculated value, which is 10. Hence, we update the table as well as the graph. Now let's consider the next vertex x. The distance from S through y is the weight of edge sy plus the weight of edge yx, that is 5 plus 9, which is 14. Since the previous value of the vertex x is infinity, 14 is updated. Next, consider the vertex z. Sy plus yz is equal to 5 plus 2, which is 7. Again, since this vertex had a previous value of infinity, the new value 7 is updated. Now, out of the vertices which are not yet made permanent, identify the vertex which has the least distance. Here it is 7. Hence, 7 is next made permanent. So now find the distance to all the vertices through Z. First, let's consider the vertex T. Since there is no path from Z to T without forming a cycle, we do not update the value. Next, consider the vertex X. The shortest distance from S to Z is 7 and the distance from Z to X is 6. So the total distance from X to S through Z is 7 plus 6, which is 13, which is better than the previous value, which is 14, and hence the value of x is updated. The next vertex with the shortest distance is T with the value 8. Hence, T is made permanent. We have only one vertex x remaining which doesn't have a permanent value. So let's try to calculate the distance of x through T. Now we know that the shortest distance from T to S is 8 and the edge weight Tx is 1. So 8 plus 1 is equal to 9, which is better than the previous value 13, and hence the value is updated. Next, we make x permanent, but all the remaining vertices are already made permanent. Hence, that's the end of the algorithm. So the last row of the matrix indicates the shortest distance of each of the vertices from the source S, and the values within the vertices represent the same. I'll be explaining the algorithm step by step in the next video. Thank you.